Hello and welcome back. Today we're going to be continuing in Chapter 10 with sequences and probabilities. Last lesson I said there were two very common types of sequences, and we went over this first one already in our last lesson, arithmetic. And today we're going to go over geometric sequences. So this is 10.3 geometric sequences. So this is an example of a geometric sequence. Can you tell the pattern? Can you tell what's happening? Here's another one. Here's another geometric sequence. And then here's a third one. So there is something that all of these have in common, and let's take a look. So the pattern here in this first sequence is that it goes 5 times bigger with each step. So you can see 5 times 5, and then that times 5, and then that times 5. Now in this one, there is a constant multiplier. If you ignore the positive and negative, you can see it's 12, 24, 48. So it is doubling. However, it is switching back and forth between negative and positive numbers. And the way to do that is to multiply by a negative. So if you continuously multiply by -2 each step, you will get the next number. I'm sorry, this one was times 5. And then what about that third one? What is the pattern there in this third one? So you can see that the number goes from -3 to 1, which would be multiplying by -1/3. So because 1/3 of 3 is 1, and then the negative changes the sign. And then 1 times -1/3 would give you -1/3, and -1/3 times -1/3 would give you 1/9. So hopefully you can see that the pattern here is that in all of these, there is something being repeatedly multiplied. That's what defines a geometric sequence. So in an arithmetic yesterday, there is something being repeatedly added. For a geometric sequence, there is something being repeatedly multiplied. That number that you're repeatedly multiplying by is called the common ratio. That is the amount being repeatedly multiplied. So that would be these numbers I wrote beneath here. So in the first one, the common ratio is 5. In the second one, the common ratio is -2. And in that third one, the common ratio is -1/3. The formula for a general term, so like how would I get a term farther out? What would be the formula? Well, if you think about, like, let's take this one. How do you get the second term? Well, you take the first term and you multiply by 5 once. And then how would you get the third term using the first term? Well, you would take the first term and you'd multiply by 5 twice. So again, to get the third term, you'd multiply by that common ratio twice. To get the fourth term, you multiply by the common ratio a total of 3 times. So you can see you always multiply by that common ratio one less time than the term number, which is why the exponent here of r is n-1. So the formula for a general term is the first term times r to the power of n-1. So for that second sequence here, the first term's -12, and the common multiplier is -2, so this would be what the formula looks like for that second sequence there. Alright, write out the first 6 terms of the geometric sequence with a first term of 12 and a common ratio of 1/2. So the first term is 12, and then to get the next term, again, since this is a geometric, this is the number we repeatedly multiply by. So 12 times 1/2 is 6, 6 times 1/2 is 3, 3 times 1/2 is 3/2, times 1/2 is 3/4, times 1/2 is 3/8, and those are the first 6 terms. Next, find the 7th term of a geometric sequence with whose first term is 5 and whose common ratio is -3. And we're going to do this one 2 different ways, just like we did yesterday in the arithmetic. The first way is we're going to actually list the first 7 terms. So I start with 5 and I just list out the first 7 terms, repeatedly multiplying by -3 until I get 3,645. Then we're going to look at a different way to do this one. And we're going to use the formula for a general term. So the formula for a general term for a geometric is this. The first term is 5, and r, the common ratio, is -3. And then, since I want the 7th term, I plug in a 7 right there for n. And then I can type that in my calculator. This is 5 times negative 3 to the 6th power. And I get that same answer there for the 7th term, 3,645. Now, is this second way faster than this first way? Well, for this one, I don't know. Maybe not. You had to list 7 numbers and find 7 numbers here. This might have been faster. This second way is definitely going to be faster if you've got a big number for n you're trying to find. All right, next, the sum. So basically, to find the sum of a geometric, the first term would be this. So the second term would be that first term times r. The third term would be that first term times r squared, and so on and so on and so on all the way to the last term. Now, the formula to find the sum, there's no nice trick like there was last time with the first and last terms. The formula comes from taking this equation and multiplying everything by r, and then taking these two equations and subtracting them from each other. Because you'll notice there are a lot of terms in common here when you subtract that you get to eliminate. It's not so important that you understand how this formula works or where it comes from, but basically here's like where it comes from is you get, subtract on this side, and when you subtract this side, you're left with very few terms, which makes it really easy to then solve for s sub n by factoring out an Sn and then dividing by that 1 minus r, and then that's how you get this formula. So it's not that big of a deal that you know where it comes from, but that is the formula right there for the nth partial sum for a geometric series. So S sub n is the sum of the first n terms, n is the number of terms, a sub 1 is the first term, and r is the common ratio. One thing to be careful of here is if r is negative, make sure you actually put in parentheses right here when you're raising it to the power of n. All right, so let's take a look at finding the sum of the first 9 terms of this geometric series. So we're told it's geometric, and you can see there is a common multiplier. 2 times 3 is 6, times 3 is 18, times 3 is 54, but you can see it's positive, then negative, then positive, then negative, which means we're multiplying by negative 3 each step. So to find the sum of the first 9 terms, you use the formula right there. The first term is 2, and r is negative 3, and n is 9. So I plug in a 2 there, negative 3 there and there, and a 9 there. Then I can simplify this. I can use my calculator. Negative 3 to the 9th power is negative 19,683, and then 1 minus that becomes 1 plus that. And then on the bottom, 1 minus negative 3 is 4, and then 1 plus that gives me that. I double the top, I divide it by 4, and I get 9,842. All right. Next, find the following sum. Now you'll notice this is our summation notation. So I'm going to write out the terms. I'm finding terms 1 through 8 and adding them together. So I plug in a 1 to get the first term. I plug in a 2 to get the second. I plug in a 3 to get the third, and so on all the way until the last term here is the 8th term is 2 times 3 to the 8th power. So this is 6, this is 18, this is 54, and that last term is 13,122. Now you will notice that this is a geometric sequence because these numbers are tripling. Okay, so to find the sum, instead of listing all 8 numbers, I can use the formula that lets me plug in the sum of the first 8 terms is the first term 6 minus, or times 1 minus r, which is 3 to the 8th power, over 1 minus 3, which you can type that all into your calculator, is 19,680. Next, let's look at a real-world situation of a geometric pattern. So a union contract specifies that each worker will receive a 5% pay increase for each year of the next 30 years. If a worker is paid $20,000 in the first year, what is this person's total lifetime salary over a 30-year period? So in the first year, they make $20,000. In the second year, you need to multiply by, to do a 5% raise, you multiply by 1.05. In the third year, you need to take the second year and multiply it by 1.05, and so on. You will be repeatedly multiplying by 1.05, all the way up to whatever we have in year 30, and our question right here is asking us to add all these numbers together. So this is the sum of a geometric series. So it's the sum of the first 30 terms. The first term is 20,000 times 1 minus r is 1.05 to the power of n, which is 30, all over 1 minus r, which is 1 minus 1.05. You'll notice I never actually have to figure out this term like we did in arithmetic. I don't actually need to find that last term to use this formula. You can type that all into your calculator once. Be careful with your parentheses and your fraction, but you would get a total earnings of $1,328,776.95. All right, now it's going to get a little weird. Find the sum of the following geometric series: 1/2 plus a fourth plus an 8, ... Now that ... is the part that's weird. Because what this is asking us to do is it's asking us to add up this string of numbers forever. Okay? Now you'll notice I wrote an equals 1 here. Where did I get that? Well, think about it this way. Let's say I'm exactly 1 mile away from home, and I start by walking half a mile. Okay, so then I'm halfway home. Then I walk half the remaining distance. Half of a half is a fourth, so I walk a fourth of a mile. And then I walk half the remaining distance, which is an eighth of a mile. And then I walk half the remaining distance, and then half the remaining distance, and half the remaining distance, and half the remaining distance. When will I get home? Well, never, because I would have to keep walking half the remaining distance forever. I would keep getting a little bit closer with every little step I take. But even though I'll never get home, when I do make it home, I will have walked 1 whole mile. Which is a little weird to think about, that I'll never make it, but when I do make it, my total will be 1. Now, here's kind of why that happens. This is a geometric pattern, except n is basically like infinity. So my starting term is a half, my common ratio in this problem is a half, but n is like infinity. And here's the weird thing about this. If you take 1/2, the number 1/2 to a really, really, really large number, this total will basically become the number 0. And then what happens is I'll get this when I plug in a 0 here, which is equal to 1. Now this part right here where I made this number 0, this is actually really dangerously close to doing calculus right now. The reason this happens involves limits, and you'll learn about those next year when you take calculus. But basically, this part of the equation, when you do an infinite sum, that part of the equation basically goes away because you will get like a 1 minus 0 here. All right? So that's why that 1 minus r to the n isn't here when you have an infinite series. Now this is only true if r is less than 1. The absolute value of r is less than 1. R has to be a number between 0 and 1, a fraction, for this to be true. So this is how you find the sum of an infinite geometric series. Now the reason r has to be less than 1 is because if r is 1, you're just adding the same number together a whole bunch of times, which is infinity. And if you try to plug in a 1 here, you get like an undefined value, so that doesn't work. If r is greater than 1, though, you get like a series where you're adding a bunch of numbers that are just getting bigger and bigger and bigger, so your total will go on forever up to infinity. However, if you do plug this common ratio into the formula, it will actually give you an answer that is absolutely not the correct answer. These do not add up to -3. So be careful when you're using this formula. An infinite geometric series only works if r is less than 1. So let's take a look at, an infinite series here. I guess there's the whole answer, but let's take a look at how I got it. So 36 plus -6 plus 1, and so on and so on. Notice that there is a common multiplier of -1/6. That is a number that is less than 1. The absolute value of -1/6 is less than 1. I plug it in the formula. That's the first term over 1 minus r. Okay, I can type this all into my calculator, and it will give me the fraction 2/16/7, which is approximately 30.857. So that's it for geometrics sequences, a little bit more with this one. So give that homework a try and let me know if you have any questions.